Bismillah ar-Rahman ar-Rahim. This is our first lecture in Physics 110, General Physics 2 for Spring 2024. For section 3, let's start by going quickly through the syllabus of this course. Our class location will be on the building F3-0130, and our meeting time will be every Tuesday and Thursday from 11 a.m. to 12 past 15 p.m. This is your instructor, Dr. Shahdi Amri. Our office hour will be set to be every Tuesday from 9:30 a.m. to 10 past 30 a.m. at the building F1, room 0101. So this course aims to develop a clear understanding of the basic of physics concept in electricity and magnetism. We will talk about Coulomb's law, electrostatic field, Gauss's law, electrostatic potential, capacitance and dielectrics, electric current, resistance, direct current circuit, and Kirchhoff's rules, RC circuit, magnetic field and magnetic forces, sources of magnetic field, and we will finish this course by electromagnetic induction. Our reference is Jung and Friedman, University Physics with Modern Physics book from Pearson Company, the 15th edition. So this course, as you know, we have 5 course learning outcomes. The first CLO is how to compute the electric forces and field due to discrete and continuous charge distribution using summation integration and Gauss's law. The second CLO is compute electric potential energy and potentials due to discrete and continuous distribution of charge using summation and also integration with application to the capacitors. The third CLO is analyze DC circuit and compute the electric parameters. The fourth is compute the magnetic force on point charges and on current carrying wires. The last CLO is applying Biot-Savart law and Ampere's law to calculate the magnetic field. Let's talk a little bit about the course policy of this General Physics 2. As you know, the course will be delivered face-to-face on the university campus for the spring 2024 semester. Attendance is mandatory for this course. If a student, for example, misses 15% or more of the classes, he will be failed in this course and you will get fail for absence rate. In case you miss it, any class of this course, and you have an acceptable excuse, so you have to contact the advising unit so that they can remove your absence. I want to talk more about the homework and the assignments of this course. At the end of each chapter of this course, homework problems will be assigned from the end of book problems of the textbook, and an online quiz will be done. Homework will be done online at home using Mastering Physics website, but the quizzes will be on the class during the last 10 minutes of the lecture. Quizzes will be computerized using Blackboard and Respondents Lockdown. So please, you are asked to use UAE Wi-Fi. No other network is allowed. There is a very important note here. Scratch paper will be distributed for each quiz, on which students must show the steps of the solution whenever it's requested. A note, in the quiz, midterm, and the final exams, students will get 0 if they did not show the steps in the multiple choice formula-based question and formula solving and problem solving questions. Writing the final answer only is not enough. So please, you are asked to develop your answers step by step. The midterm and the final exam will be done face-to-face on the campus. Formula and equation sheets are not allowed during the exam or the quizzes. The makeup policy for this course. There is no makeup for the homework or the quizzes, whatever the reason or whatever the excuse. However, at the end of this course, we will drop the lowest 2 grades of the homework and the lowest two grades of the quizzes to compensate any excuse for the absence. So I repeat, there is no makeup for the homework or the quizzes, whatever the excuse. At the end of the course, 2 homework and 2 quizzes will be dropped by the end of the semester to compensate any excuse for absence. The lowest 2 grades of the homework, the lowest 2 grades of the quizzes will be dropped. If a student misses the final exam or the midterm exam with an acceptable excuse, and the excuse is proved by the advising unit, in this case, for the midterm exam, we can set for you a makeup exam. However, for the final exam, you will sit for the makeup exam of the final during the next semester. Let's talk about the course evaluation and grading distribution for this course. The homework will be assigned 15% of the total grade. And we have a homework at the end of each chapter, plus first homework about physics primer. The quizzes, the total grade of the quizzes will be 15% of the total grade. At the end of each chapter, we have a quiz, as we said before. Regarding the midterm, the grade of the midterm will be 30%. Our midterm will be on the 7th of March, 2024, from 7 p.m. to 8 p.m. The final exam will be 40%. On the 4th of May, 2024, from 8:30 a.m. to 10:30 a.m. So you see here that we have 1 hour for the midterm and 2 hours for the final exam. We try to set for you a schedule for this course. Our semester is composed of 16 weeks plus final exam. So you see here that your first homework will be assigned during the 2nd week. In this course, we will treat, or we will explain from chapter, or we will study from chapter 21 to chapter 29. Chapter 21 is electric charges and electric field. This is the longest chapter of the course. We will stay with this chapter for 4 weeks. Okay, 4 weeks. So it's very important for you to track the informations and to follow the instructions of the course of the instructor. Okay, so this is an overview about the syllabus. Now we would like to start our first lecture. Our first lecture will talk about electric charges and electric field. In this lecture, we will talk about how to study the electric charges and the charge conservation. We will see how objects become charged. We will calculate the electric force between objects using Coulomb's law. Let's start by the introduction. As you know, water makes life possible as a solvent for biological molecules. What is the electric properties allowing the water to do this? We now begin our study of electromagnetism, one of the 4 fundamental forces. We start with electric charges and look at the electric field. As you know, and as you have learned, 2 positive charges or 2 negative charges repel each other. A positive charge and a negative charge attract each other. That means if we have a positive or negative charges, they will repel. Different charges, they will attract. This Picable law shows some experiment in electrostatics, and we will talk by the different processes of charging. The first process is charging by contact. You can see here, if we have an uncharged plastic rod is approached to another uncharged plastic rod, there is nothing to happen. However, when we rub the plastic rod with the fur, the plastic rod will be charged negatively. Charged negatively means gain some electrons from the fur. Now, if we have two charged rods with a negative charge and they are approached near to each other, what happened here? They will repel because we said two positive or two negative charges repel each other. Let's move to the second experiment. We take now a glass rod, which is initially uncharged, and we approach this glass rod to another uncharged glass rod. Nothing to happen. However, when we rub the glass rod with the silk, the glass rod will be positively charged. That means we lose some electrons, and these electrons will be transferred to the cell. Now, if we have two charged glass rods and they are approached to each other, so here we have a repulsive force between these two glass rods because their charge is positive. Now imagine that we have a plastic rod with a negative charge and a glass rod with a positive charge. These two rods are approached to each other. So here there is a repulsive force between them, attractive force, because positive charge and negative charge attract each other. This kind of charging is called charging by contact. There is a contact between the first object, plastic rod, and the third. There is a contact between glass rod and the silk. An example of this is the laser printer, where there is a force between the charged bodies. Let's move now to talk a little bit about the particle of the atom. What are the particles of the atom? What are their charges? And what are their masses? The atom is composed by a proton and nucleus. These two particles make up the tiny, dense nucleus, which is surrounded by a third particle called an electron. The proton is charged positive. Its mass is around 1.673 times 10 power negative 27 kg. The neutron has no charge, so the neutron is in charge. Its mass is 1.675 times 10 power negative 27 kg. What about the electron? The electron is negatively charged. Its mass is 9.109 times 10 power negative 31 kg. So these three particles make up the atom. You see here that in the nucleus, we said the proton is positively charged and the electron is negatively charged. Negative and positive charges, they will attract each other. The electric attraction between proton and electrons holds the atom together. Atom and ions. A neutral atom has same number of proton as electrons. As we said, proton is positive, electron is negative. If we have the same number of proton and electron, that means the same number of positive and negative charges. The total charge of the atom is 0. And in this case, it's called a neutral atom. Imagine now that some electrons are removed from the atom. In this case, the total number of protons exceeds the total number of electrons. That means the positive charges in the atom exceeds the negative charges of the atom. In this case, the atom will be charged positively, and we talk about positive ion. In the opposite side, if the atom gains some electrons, one or more, in this case, the number of electrons exceeds the number of proton. That means the number of negative charges exceeds the number of positive charges in the atom. In this case, we talk about negative ion. We take an example of this. A neutral lithium atom has 3 protons, that means 3 positive charges, 4 neutrons, and 3 electrons. That means 3 negative charges. 3 positive charges plus 3 negative charges gives 0 in the charge. So the electrons equal protons, 0 net charge. But now, if the lithium atom lose one charge, one negative charge, one electron, so the number of protons will stay the same, 3 plus 3, but the number of electrons will be 2, and the total charge is -2 for the electrons. What is the net charge of the atom? The net charge of the atom, 3 plus 2 minus will be plus, and we talk about positive ion. But on the opposite side, when the lithium atom gain 1 electron, so the total number of protons is 3 plus 3, and the total number of electrons will be 4, and the charge for the electrons will be -4. In this case, the net charge is -1, and we talk about negative ion, Li-. Let's talk about conservation of charge. The proton and the electron have the same magnitude of charge. The magnitude of charge of the electron or proton is a natural unit of charge. All observable charges is quantized in this unit. So, what means this? The magnitude of charge of the electron and the proton is the same. It's equal E, something that we call E, unit of charge. This unit of charge is equal 1.6 times 10 power -19 Coulomb. So the unit of charge E equal 1.6 times 10 power -19 Coulomb. Okay? For the proton, the charge of the proton is equal plus E. For the charge of the electron, it's equal minus E. It's okay? The universal principle of charge conservation states that the algebraic sum of all electric charges in any closed system. How is it? If we have a closed system, the algebraic sum of all the electric charges will stay the same. That means it's constant. And we call this principle of charge conservation. But here, don't forget that we are talking about closed system. Okay? Let's move through a quick quiz. If you rub an inflated balloon against your hair, the two materials attract each other. What are these two materials? We are talking about the balloon and the hair. As shown, is the amount of charge present in the balloon and your hair after rubbing is the same, less than the amount of charge present before rubbing, or more than the amount of charge present before rubbing? Let's refer to the universal principle of charge conservation. We said that the algebraic sum of all electric charges in any closed system should be the same, must be the same. Here we have our system is composed by the balloon and the hair. Is there any other particle in interaction with these two materials? No. That means it's possible that some charges from the hair moves to the balloon or the opposite. However, the total number of charges will stay the same. So what we can say, the amount of charge present in the balloon and your hair after rubbing must be the same according to the principle of conservation of charge. Then, let's talk about conductors and insulators. These are the different types of material according to their conductivity. A conductor permits the AC movement of charge through it. An insulator does not. An example of the conductors, most of the metals, the iron, the copper, and human are also good conductors, while most non-metals are insulators. An example of the insulators, wood, for example. Let's talk about the semiconductors. Semiconductors are material intermediate in their property between good conductors and good insulators. Sometimes in some conditions they are conductors, and in other conditions they are insulators. Let's take an example, the example of silicon. Silicon is a semiconductor. Okay? At high temperature, the silicon is a good conductor. However, at low temperature, the silicon is an insulator. Okay, so based on some condition, the semiconductors can be good conductors and can be good insulators. Now, after talking about charging by contact, we will talk about charging by induction. In the figure below, the negative rod is able to charge the metal ball without losing any of its own charge. This process is called charging by induction. In this figure, we have a metal ball initially charged. That means the total number of positive charge is equal to the total number of negative charge, and the net charge of this metal ball is 0, standing on an insulator. Now, let's come back to our plastic rod, which is negatively charged. We approach this rod to this ball. What happened to the charges of the ball? The positive charges will be attracted by this negative rod, by the negatively charged rod, and the negative charges will move to the other side because they will be repelled. Negative charges on the rod repel electrons, creating a zone of negative and positive induced charges. Okay? Then the ground wire is connected to this ball. What happened to the negative charges? The negative charges will flow through this ground wire and will be evacuated. What is the total charge of the ball after approaching this negatively charged rod and after connecting with this wire, this ground wire? The total charge will be positive. And we will talk about positively charged ball. Okay? Is there any contact between these two materials? No, there is no contact. Here we talk about charging by conduction, by induction. Let's see the net charge of the plastic rod before and after this phenomenon. There is no difference. So we can say that the negatively charged rod is able to charge the ball without losing any of its own charge. Okay. And then let's move to the point of charge, definition of point of charge. When we say charge, we really mean a charged object. A point of charge is a particle of 0 size. That means very tiny particle carrying a charge. For example, electrons or protons. Electrons and the protons are considered as point of charge because their size is very reduced size and they have positive or negative charge. So we will call them point charge. More precisely, particle separation is much larger than the particle dimension. This is what means 0 size. We can have few charges separated by a distance or many charges spread like touching each other. In the first case, we talk about discrete charge distribution when they are separated by a large distance. We talk about discrete charge distribution. In the second case, we talk about continuous charge distribution. Later on, we will see the distributions over the length, the surface, and the volume. And we will talk in more details about the continuous charge distribution. Now, let's talk about Coulomb's law. Coulomb's law is a law permitting the calculation of the magnitude of electric forces between 2 points of charge. And this law states that the magnitude of electric force between 2-point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. The mathematical expression of the Coulomb's law is F, the electric force, is equal to K, absolute value, Q1, Q2, divided by R squared. K is called Coulomb's constant. Coulomb's constant is equal to 1 over 4 pi epsilon naught. Okay? Epsilon naught. And it's equal to 9 times 10 power 9 Newton meter squared divided by Coulomb square. Good? Okay, good. Let's continue. According to Coulomb's law, if we have positive and positive charges, of course, as we said before, there is a repulsive force. Let me explain here. Okay. If we have positive and positive charge, what happened between them? There is a repulsive force because they have the same sign of charge. Let's say this is particle number 1 and this is particle number 2. Point charge number 1, point charge number 2. Okay. What do we call the first force applied on the charge 1? It's called the force applied by the second point charge on the first point charge, and don't forget that the force is a vector. The second force to the right is called F1 on 2, and don't forget also that it's vector. If we take, so according to Coulomb's law, the magnitude of F1 on 2 will be equal to the magnitude of F2 on 1. They have the same magnitude. What is this magnitude according to Coulomb's? It's equal to K, absolute value of Q1 multiplied by Q2 divided by the distance between them. What is our distance? The distance between the 2-point charges is following. It's called R. Okay? However, these two forces, they have opposite direction. So we can say F1 on 2, that means the force applied by the charge 1 on the charge 2 is equal to minus the force applied by the charge 2 on the charge 1. They have same magnitude, but opposite direction. Good. Very good. That's nice. Okay. So these two results are also valid when we have different charges. Negative, that means two negative, or positive and negative. So as we said, Coulomb's constant is equal 1 over 4 pi epsilon naught. Its unit in the size system. Newton meter squared by Coulomb squared. The quantity or the constant epsilon naught is called permittivity of free space, and it's equal to 8.85 times 10 power minus 12 Coulomb per Newton meter squared. Good. A quick quiz. An object A has a charge of +3 microcoulomb, and an object B has a charge of +6 microcoulomb. Which statement is true? Let's draw the situation. We have positive 2 microcoulomb. Let's say this is charge A, and +6 microcoulomb also. And let's say this is a charge B. Positive and positive charge, they will repel each other. This is the force applied by the particle A on the particle B, and this is the force applied by the particle B on the particle A. Good. What we said in the previous slide? The two forces, they have the same magnitude, but opposite in direction. So which statement is correct? FA on B is equal minus 3 FB on A. FA on B is equal minus FB on A. 3 FA on B equal minus FB on A. Be careful here before answering this question. Be careful. 2 microcoulombs, 6 microcoulombs. There is a factor of 3 between them. So, okay, yes. QA equal 3 QB. In the question, did we ask it about the comparison between the two charges or the comparison between the two forces? He's asking about the two forces. The two forces, we said, they are equal in magnitude, but opposite in direction. FB on A. And as a vector, FA on B equal minus FB on A. It's okay? So please don't be confused here. The question is asking about the forces, not the charges. When he's asking about the charges, of course, there is a factor of 3 between the two charges, but he's asking about the force. So the correct answer is S. They have same magnitude. Why the answer B, the answer A is wrong? Because it's not the same magnitude. Answer C also is wrong because they don't have the same magnitude. They have the same magnitude, but opposite in direction. Opposite in direction means negative sign. It's okay? Good, let's move. Okay, when we take an example, this example is a comparative study between electric force and gravitational force, which is example 21.1 in the book. An alpha particle, the nucleus of a helium atom, has a mass of m equal 6.64 times 10 power negative 27 kg, and the charge q equal plus 2e, that means 3.2 times 10 power negative 90. Compare the magnitude of electric repulsion between two alpha particles with the gravitational attraction between them. The question here is what? Is a comparison between the gravitational force and the electric force. Good. Let's start to solve. But at first, let me draw the two alpha particles. Alpha particle is a positive particle. Is an interaction with another alpha particle. Let's say this is particle A, or particle number 1, and let's say this is particle number 2. It's almost the same. It's the same particle. Okay. The question compared between the electric forces and the gravitational force. You see here that we have two positive alpha particles. So the force between them is repulsive. F2 on 1, and this is F1 on 2. Okay. What is the magnitude of these forces? F equal K, Q1, Q2 in absolute value divided by R squared. R is the distance between them. When we compare this electric force with what? With the gravitational force. What is our gravitational force? The gravitational force is an attractive force. Also, they have the same magnitude but opposite in direction. This is the gravitational force. This is the gravitational force. Okay. According to Newton, the gravitational force magnitude equal a constant called G multiplied by M1 without absolute value, sorry. The mass is M2 divided by R squared. You see that in the two expressions of the force, we have R. In the question, did we have any information about R? No information about the R. So what we must do in this case? In this case, no information about R, but we have information about the constant. Constant G equal 6.67 times 10 power negative 11. Good. So what we're gonna do in this case? In this case, we will do the following. to compare between the two forces or two quantities, we will divide them. Okay. If it's too much greater than 1, that means the electric force is greater than the gravitational force, and the opposite case also. If it's lower than the 1, so in this case, the gravitational force is greater than the electric force. Let's write this quotient. In this case, we will write K Q1 Q2 divided by R squared. All of them divided by the gravitational force, which equal G M1 M2 divided by R squared. So in this case, we can cancel this R squared, and the answer will be K over G multiplied by the absolute value of the product between the two charges, Q1, Q2, divided by M1, M2, the product between the two masses. Okay, however, the two particles are alpha particle. So Q1 is equal to Q2, same particle, and M1 equal M2, because we talk about same particle, two alpha particles. Okay, so in this case, electric force divided by gravitational force will be K over G multiplied by Q squared over M squared, which is equal 9 times 10 power 9, as we said before, divided by 6.67 multiplied by 10 power negative 11. This is multiplied by 3.2, the charge of alpha particle in the question, 3.2 times 10 power negative 11, 3.2 times 10 power negative 19, divided by their mass, the mass of the alpha particle, 6.64 times 10 power negative 27. So the result, our result will be, yeah, I will give you some seconds or some minutes, some seconds, 30 seconds to give me the result. Good. So our result will be 3.1 times 10 power, yeah, times 10 power 35. Imagine that, 10 power 35. What's the unit? Without unit, because we divide force by force. What we said if the gravitational force, if the electric force divided by the gravitational force gives a result, and this result is greater than 1, too much greater than 1, in this case, we will neglect the gravitational force. Too much big compared to 1. So in this case, the electric force is too much greater than the gravitational force. So as a conclusion, we neglect FG. We neglect FG. Okay, so in this chapter, we will not talk about the gravitational force, because the gravitational force, it's too much small when compared to the electric force. We should multiply by 3.1 times 10 power 35 to get the electric force. Okay. Now let's move to the superposition principle. The superposition principle, the principle of superposition of forces, states that when two charges exert at the same time a force on the third particle of charged particle, the total force acting on that charge is the vector sum of the forces that the two charges would exert individually. This principle holds for any number of charges. So imagine now that we have one particle number 1, particle number 2, Okay. Both of them, let's say one positive and one negative. Okay, let's change it. One positive and one negative. And we have a third point of charge, which is positive. The charge 1 exert a force on the charge 3. The force is outward, it's repulsive. So this is the force F1 on 3, it's repulsive force. The charge 2 exert a force on the charge 3, and this force is attractive because they have different sign. So this is F2 on 3. Good. What is the total force applied on the charge 3? According to this principle, the superposition principle of the charge of the forces, it's their vector sum. So we can draw the parallelogram formed by these two forces or these two vectors, and this is our vector F3. It's the vector sum of the forces applied on this charge by these two charges and divided. So it's the sum of the force exerted by the particle 1 on the particle 3 plus the force exerted by the charge 2 on the charge 3. So let's repeat this principle, it's very important. When two charges exert force simultaneously on the third charge, the total force acting on that charge, that means charge number 3, is the vector sum. It's the vector sum of these two charges, of the force that the two charges would exert individually. Now, if we add another force, another point of charge, 0.4, for example, or 5, or whatever, so the total force exerted on the charge 3 must be the sum of all these forces. Good. It's a clear piece. Good. Let's take an example. What force does Q1 exert on Q2? And what force does Q2 exert on Q1? Gravitational force are negligible. In the first case, we have two charges. They are in the same sign or different sign. They have different signs, so the force between them is attractive. This is F exerted by 2 on 1, and this is F exerted by 1 on 2. Okay? So according to Coulomb, these two forces, they have the same sign, the same magnitude, but opposite in direction. Okay? So this is the free body diagram for the charge Q2. The force is directed to the left. And this is for the charge Q1, the force is directed to the right. We take an example, another example. If we have in this situation 3-point charges, Q3 is located at the origin and has a charge 5 nanocoulomb. Q1 is located at a distance of 2 centimeters in the positive x, and its charge 1 nanocoulomb. Q2 is minus 3 nanocoulomb, and it's located 4 centimeters far from Q3 in the positive direction. The question, what is our question here? What is the total force applied on Q3? Okay, good. That's a very good question. It's direct application of superposition principle. Okay, as usual, I would like to draw the free body diagram. We said this is, let's see, it's positive, and negative. So this is our Q3, and this is our Q1, and this is our Q2. Good, very good. Okay, let's start by the force applied. Okay, our question is what? Our question is what is the force applied on 3? What is this force? Let's start by the first charge. F1 Q1 exert a force on Q3. and this force is repulsive because both they have the same sign. Both of them are positive. So this is F1 on 3. Good. Let's see now the charge Q2. Q2 is negative, so the force is attractive between 3 and 2. Good. What is the total force exerted on Q3? It's the sum of, let's write here, it would be the sum of F1 on 3 plus F2 on 3. So to get F3, we should calculate F1 on 3. We should calculate F2 on 3. So you see here in this example that all the charges lies along the x-axis. So how many components we have for this force? We have just one component, x. So we can write F3, x component, and here x component. What about the y component? Y component of the forces are equal, are zeros. Why? Because all charges along x on x-axis. Okay, good. Let's start now with the calculation of the first. The calculation of the first. We will start by the following. Okay, let's start by green. F1 on 3 in magnitude according to Coulomb's law, it's equal K, Q1, Q3 in absolute value divided by the distance between 1 and 3 squared. Good. So it will be 9 times 10 power 9 times Q1 how much? And Q3 how much? Q1 is 1 nanocoulomb, Q3 is 5 nanocoulomb. 1 nanocoulomb, that means 10 to the power negative 9 multiplied by 5 nanocoulomb, that means 10 to the power negative 9 divided by the distance between them. I think it's 2 centimeter. 2 centimeter, that means 2 times 10 power negative 2. Why we multiply it by negative 2? By 10 power negative 2, because we have to convert to the meter. And we multiply it also the charges by 10 power negative 9, because we have to convert to Coulomb, forget it's squared. We will do the same thing. Okay, what will be the result here? What will be the result? Okay, good. Let me try to calculate and to use the calculator with you. Okay, good. Where is it? So what we said 9 times 10 power 9, this is the constant K, multiplied by the absolute value. Okay, we take as it is positive, so that means 10 to the power negative 9 multiplied by 5 times 10 power negative 9, and it's divided by what? Divided by 0.02 squared. What is the result? Oh, no. There is a mistake. No, there is a mistake in the calculation. So what we said it's 9 times 10 power 9 multiplied, oh, good, multiplied by 10 to the power negative 9 multiplied by 5 times 10 power negative 9 divided by 0.02 squared. Our result is 2.25 times 10 power 13. What's going on here? No, it's not that. 9 times 10 power 9 multiplied by 10 power negative 9 multiplied by 5 times -9 also, divided by 0.2 squared. Good. So this is our result. It's 1.125 times 10 power -4. 1.125 times 10 power -4. What's the unit of the force? As you know, it's Newton. Good. Let's talk about the second vector, the second magnitude, F2 on 3 in magnitude is equal the same expression KQ1, Q3, Q2, KQ2, okay, Q2, Q3 in absolute value divided by the distance between 2 and 3 squared. Good. So it will be equal 9 times 10 power 9 times Q2. He said it's -3, -3. So multiplied by the absolute value of -3 times 10 power -9 times Q3 is 5 times 10 power -9. And it's divided by the distance from Q2 to Q3, the distance is 4 centimeters. Okay, so divided by 4 times 10 power -2 squared. The result, good. So our result will be, so here instead of 10 to the power 9, we will write 3. Okay, instead of 0.2, we will write 4, and the result. The result is 1.69, 1.69 times 10 power, sorry, what's going on? Oh, let me repeat. 9 times 10 power 9. This is for the K. The first charge, we take, of course, the absolute value. That means 3 times 10 power -9 nanocoulomb multiplied by 5, the third charge, times 10 power -9 divided by 0.04 squared. And the result is 8.44, 8.44, 8.44 times 10 to the power -5 in Newton. Okay, so we got the first force, we got the second force. This force, if we talk now about the component, this is a magnitude. If we talk about the component, okay, let's talk about the component of these two vectors. F1 on 3, F1 on 3, it's directed to the -x. So when we talk about the component, we will add a negative sign. We will add a negative sign. Why this negative sign? Because we are talking about we are talking about a vector directed in the opposite direction of the x. That means it's directed to the -x. What about F2 on 3? F2 on 3 along x, it's a positive also. It's positive. Why? Because it's directed to the right. It's directed to the positive x direction. So here it's a positive. When we talk about vector, okay, when we talk about vector, the vector F1 on 3, it's along -I. That means multiply here by I. It's a long negative I. Okay, when we talk about the vector, so we will add here I. Good. Now we got the two vectors, so we can get their sum. Their sum is what? Just using the superposition principle. So F3, as we said, it's equal F1 on 3 plus F2 2 on 3. So it's equal minus 1.125, 125 I plus plus what? 8.44. No, sorry, we forgot 10 to the power. Yeah, times 10 to the power negative 4 plus 8.44 times 10 to the power negative 5. Both of them belong I, and there the unit is a Newton. And this is our total vector, so we can get to it. It's okay? Good. Now let's move. Let's move. Calculate the force acting on the charge Q1. All the charges are fixed in the position as shown in this way. Calculate the force acting on the charge Q1. According to Coulomb, the force exerted on Q1 is attractive or repulsive. Different signs of it. This is F2 on 1 exerted on Q1. Okay, according to Coulomb's, F2 on 1 is K Q1 Q2 over R squared between 1 and 2. Direct application, so it will be 9 times 10 power 9 multiplied by absolute value of Q1, how much? Q1, 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 Q1. Okay, negative 3 microcoulomb 10 to the power negative 6 multiplied by 2, what is it? 2 microcoulombs 10 to the power negative 6. And it's divided by the distance d between these two charges. The distance d is 0.4 meter squared. Okay, let's do the calculation. So it's 9 times 10 power 9. This is for K, multiplied by 3, because we will take absolute value, times 10 power negative 6, because we are talking about microcoulomb, multiplied by 2 times 10 power negative 6 also, and it's divided by 0.4 squared, 0.4 meter squared. The result, 0.34 Newton. Good. Is it a long x or a long y or negative x or negative y? So this is F2 on 1. This is as a magnitude, as a magnitude. Let's, if we want to write this force as vector, so it's directed to the positive x direction. So we will write, we will draw this arrow, and we will write here it's longer I. Good, good, good. So this is, we take another example. We take another example, Coulomb's law. Now we will talk about superposition principle. Two equal positive charges, Q1 equal Q2 equal 2 microcoulombs, are located at x equals 0, y equal 0.3 meter, and x equals 0, y equal minus 0.3 meter respectively. So we can see that Q1 and Q2 are equidistant from the origin along y. But both of them, they don't have any component along x. They don't have any coordinate along x. What are the magnitude and the direction of the total electric force that Q1 and Q2 exert on the third charge, capital Q, equal 4 microcoulomb at x equals 0.4, y equals 0. So I would like always to draw again the situation. So what we have x and y axes. X and y axes. This is our y axis, and this is our x axis. He said that there is two charges, positive here, Q1, and another charge, Q2, is here. Okay, But there is another charge. The third point charge is Q, which is positive also. Positive also. This is capital Q. Good. The question is, what is the force applied on capital Q? This is our question. He's asking about the vector, its magnitude, and its direction. Okay. Let's start step by step. As we said before, Q1 exert a force on capital Q. This force is repulsive because the two charges are positive. So this is the force exerted by one on capital Q. Charge Q2, the same thing. We exert a force on the charge Q, which is also repulsive because the force is the two charges are positive. He said the distance between the two charges is 0.5. The distance between the two charges is 0.5. Here, 0.5 meters. And the distance from capital Q to the origin is 0.4. And this distance. This angle is called alpha or theta. What he said here? He said alpha. This angle also alpha. This angle also alpha. And this angle also alpha. Good. According to the superposition principle, the total force exerted on capital Q is the force, the vector sum of the two forces. So it will be equal F1 on Q plus F2 on Q. That's nice. Good. So our question, before the question, you see here, this is our y-axis. Okay, the same. Okay, you see here that the force F1 on Q has two components, one along X and one along Y. The same thing for F2 on Q has two components, one along X and one along Y. Yes or no? Good. So let me draw with another color. So this is the component F2 on Q along Y. And this is along X. Okay, it's clear, I think. It's clear that it has two components. Okay, in this case, we should calculate the X component of the total vector and the Y component of the total force. We will start by X component along X axis. What do we have? The same expression of the force, but now we will talk about the X axis. The X component will be equal F1 on Q plus, sorry, it's not absolute one. Along X component plus F2 on Q along X also. Good, good. Okay, so our question comes back to the following. What is the X component of this vector? What is the X component of the second? Let's start by the first. For F1 on Q along X, according to the definition of the component of the vector, it's equal the magnitude of the vector itself multiplied by cosine of alpha. Alpha is the angle between the x-axis and the force multiplied by the unit vector I, because we are talking about the X component. From where we got the magnitude of the vector itself? From Coulomb's law. So it's equal 9, okay, Q1 capital Q absolute value divided by the distance from 1 to Q, and this distance is squared, multiplied by cosine alpha. As we know, cosine alpha is the adjacent over hypotenuse. This is clear. We are talking about this vector. What is the adjacent of this angle? Alpha is the same here. What is the adjacent of this vector? The adjacent of this vector is 0.4 divided by 0.5 hypotenuse. We have here right angle triangle. So it's 0.4 divided by 0.5. Okay, And of course, it's along I, because we are talking about the x-axis. Very good. Okay, good. So let's do the calculations. So it will be equal k, which is equal 9 times 10 power 9 times q1. How much q1? q1, he said in the figure 2 microcoulomb. q3, capital Q is 4. 2 microcoulomb. Of course, we take the absolute value and we take the positive. Micro, that means -6, times 4 microcoulomb times 10 power -6, divided by the distance from Q1 to capital Q, which is equal to 0.5 meter, and this is squared. Don't forget that we will multiply by cosine. Our cosine is the adjacent 0.4. 0.4 divided by 0.5. 0.5, sorry. And our result is 0.23, 0.23. So it's 0.23 Newton. 0.23 along which axis? Along the x-axis, positive x-axis, Newton. So this is for F1 on Q along x. What is this vector? This vector is the following. Let's draw with another color. For example, let's take this color, for example. Okay, so this is, we are talking about this vector. This is the x component of this vector. Okay, this is the x component of this vector. Now let's move to the second vector. As we see here, this is our F2 on Q, and it has an x component in the same direction. Is it in the same magnitude? Yes. Why? Because Q1 is 2 microcoulomb, Q2 is 2 microcoulomb. The distance between Q1 to capital Q is 0.5. The distance from Q2 to capital Q is 0.5. Same distance, same charge, same sign, everything is the same. So they have the same x component. They have the same x component. Okay, so it's equal F2 on Q along x. What is this vector? Is it this? It's the same direction and the same magnitude. Okay, clear this point? So they have the same direction and the same magnitude. Now what about FG? FG along x. FG along x. We said it's the sum of the two components. So it's 0.23i plus 0.23i also. So which is equal to 0.46i Newton. This is the x component. Now let's move to the y component along y. Before going through the calculations, let's see this figure. Along y, the first vector F1 on Q has a y component downward. The second vector F2 on Q has a component upward. One upward, the second downward. What about their magnitude? Their magnitude is also the same because we have the same angle. The same magnitude of F2 on Q and F1 on Q. So we can write that F1 on Q as vector along y and F2 on Q as component, as y component, have same magnitude, but opposite direction. Opposite direction. So their sum, so that means FG along y, the y component of the total vector, is zero, is zero. Why? Because the two vectors, they have the same magnitude, but opposite in the direction, they are somewhere zero. So now what about the total vector fg? Fg will be equal 0.46 I only. There is no y component because the y component will be cancelled. It's okay? So we can see that our vector is along x, positive x. Its magnitude is, this is its direction, its magnitude is 0.46 Newton. That's very nice. So we are done with this example. I think it's easy and possible to do by yourself. Now let's move to another example. In this example, we said that we have a charge Q1 in the amount of charge of Q1 and Q3 are equal to 5 microcoulomb, and we have another charge located at the origin, which is equal Q3 equal to minus 2 microcoulomb. The question is find the resultant force exerted on Q3, and we have an information, the distance between Q2 and Q3 is A, and the distance between Q1 and Q3 is square root of 2A. Good, good. As usual, I would like to repeat the figure by myself to understand better. Good. So we said that we have a y-axis and we have an x-axis. At the origin, we have a charge. This charge is minus 2q, minus 2, q2. On the negative y, we have a charge. This charge is q1. And here we have q3, which is positive. Okay, the distance between q2 and q3 is a, and this distance is the square root. The question, what is the total force exerted on q3? That means he's asking about f3. According to the superposition principle, it's equal to the sum of the of f1 on 3 plus f2 on 3 as vectors. Let's try to draw these vectors. f1 on 3, both of them are positive, so the force is repulsive, so it's outward. So this is f1 on 3. It makes an angle, let's say theta or alpha, what we said here. We said anything, say this is angle theta, and this is our angle theta. The distance from Q1 to Q3 is square root of 2 multiplied by A, while the distance from Q2 to Q3 is A only. Now let's talk about this second vector. The second vector is F2 on Q, so it's we see that the two forces, the two charges have different signs, so the force is attractive. So this is F2 on 3. So our question is, come back to the point. But before answering this question, we see that F1 on 3 has two components, one along X and the second one is along Y. So we must write the same equation along X and then along Y. Let's start by the X component. Along X-axis, what do we have? We have F3 along X equal, let's write as vectors, F1 on 3 along X as vector, as component, plus F2 on 3 as component also. Okay, but according to the figure, okay, along X, good, good. According to the figure, so our question comes back to the following quantities. F1 on 3, let's change the color. Let's write green, for example. F1 on 3 is what? F1 on 3, X component of this vector. So it's the magnitude of the vector, F1 on 3, multiplied by cosine theta, multiplied by the vector I. But here, don't forget always theta with respect to the x-axis, to positive x-axis. Okay, good. From where we got this magnitude? From Coulomb's law. So it's K, U1, U3 in absolute value, divided by the distance between 1 and 3 squared, multiplied by cosine theta, multiplied by the unit vector I of the x-axis. So it will be K 9 times 10 power 9 times Q1. How much? Q1, he said it's 5 microcoulomb. 5 times 10 power microcoulomb, that means -6, times also 5 microcoulomb for Q3 minus 6, divided by the distance between Q1 to Q3, which is equal square root of 2a, and a, he said, is 0.1 meter. So square root of 2 multiplied by 0.1 meter. Both of them are squared, multiplied by cosine theta. Cosine, we don't have any information about theta, but we know that cosine theta, theta is the adjacent divided by the hypotenuse. That means a divided by square root of 2a. That means 1. Let's write a divided by square root of 2a. We have this a and a, they will cancel each other. So don't forget that it's a long vector I. Okay. What is the result? Okay, according to the calculator, you can get that 9 times 10 power 9 multiplied by 5 times 10 power -6 times 5 times 10 power -6 divided by square root of 2, okay, between brackets, square root of 2 multiplied by 0.1, multiplied by 0.1, it's squared, and all of them are multiplied by the cosine, which is equal 1 over square root of 2. Good. And our result is 7.95 7.995 I Newton. Good. So this is the x component of the first vector. Okay. Now let's talk about the x component of the second vector. X component of the second vector is the following. F2 on 3 log x is equal the magnitude of the vector F2 on 3, and we said, we repeat that, we got this magnitude from Coulomb's law, multiplied by cosine theta, multiplied by the vector I. This is the definition of the component. Good. So let's write, it will be K, absolute value Q2, Q3, the product between the two charges, divided by the distance between 2 and 3 squared, multiplied by cosine theta. Cosine theta. Let's say this is theta 1 and this is theta 2 of the second vector, and this is the vector I. Good. It will be 9 times 10 power 9 multiplied by the absolute value of Q2. How much is that? Q2 minus 2. Minus 2 negative 2 microcoulomb, that means 10 power -6, multiplied by 5 times 10 power -6, absolute value, divided by the distance between them, which is equal 0.1 squared. And don't forget the cosine. Theta in this case, we said it's with respect to the x-axis, so that means from the x-axis to this vector, this is theta 2. Okay, so how much? It's 180 degrees, multiplied by cosine 180. And don't forget that it's a long I. Okay, so this cosine 180 gives us a negative sign. That means our vector is directed to the negative x. Okay, so what will be the result? So let's try to calculate. So it will be 9 times 10 by the same way, power 9 multiplied we take the absolute value, that means we will take it positive, times 10 power negative 6, multiplied by 5 times 10 power negative 6 also, divided by 0.1 squared, and don't forget that we will multiply by negative 1. Okay, so we will keep negative 1. Okay, we will keep this negative 1. Sorry, we did a mistake. Where is the mistake? Okay, forget the bracket. Alles. Okay, 0.1 squared. So this is our result. It's 9. So our vector, our x component of the vector f2 on 3 log x is minus 9i. Okay, minus 9i. So what is our total vector now? Our total vector is, that means the x component of f3 is how much we said? We said it's 7.95 7.95i minus 9i. Okay, so how much it will be? 7.95 minus 9, so it's 1 point negative 1.05 I Newton. So this is the x component. Now let's talk about the y component. We will repeat the same steps, but along y. Along y, we will try to calculate the first component, f1 on 3 along y. So it's f1 on 3 as magnitude multiplied by sine theta 1 j. Okay, the sine is the same, opposite divided by adjacent, so it will be k q1 q3 an absolute value divided by the distance between r1 to 3 squared multiplied by sine theta. Theta is what? Well, theta 1 is what? This is theta 1. Sine theta is the opposite, a divided by square root of 2a. The opposite a divided by square root of 2a, so that means 1 over square root of 2j. Good. So what is the result here? Yeah, what is the result? So let me write. 9 times 10 power 9 times q1 and q3 are both 5 times 10 power negative 6 times 5 times 10 power negative 6 divided by square root of 2a, square root of 2a, yeah, square root of 2 multiplied by 0.1. Both of them are squared, and this is multiplied by adjacent 1 over 1 over a, and a is 0, square root of 2, square root of 2. So the result is the following: 7.95 j Newton. Good. Now let's try to calculate the second vector, the x component of the second vector. The x component of the second vector, f2 on 3 along y, it will be 0. Why? Because sine 180 equal 0. So in this case, we can get f3 along y, it will be equal only 7.95 j. 7.95 j, and the unit is in Newton. Now we got the x component of the vector f3 and we got the y component of the vector f3. So f3 as vector, it will be the sum of these two components. So negative 1.05 I plus 7.95 j. This is our vector. Okay, this is our vector. We are done with this vector. Now let's try to calculate the magnitude of this vector. It's f3 equal square root of minus 1.05 squared plus 7.95 squared, which is equal. The direction of this vector is, let's say it's alpha, tan inverse of the y component divided by the x component. The y component 7.95. The y component is minus 1.05, which is equal. Okay. For the magnitude, we said it's the square root of minus 1.05. It's squared, that means the minus, no need to write it, plus, not that, yeah, plus square 7.995 squared. Okay, so it will be, no. So it will be 8.01 or 02. 8.02. 8.02. Sorry. 8.02. Good. What about the direction? The direction, it's tan inverse of 7.95 divided by minus 1.05. So it's negative 28.5. Negative 82, sorry, not 20. Negative 82.5 degrees. However, should we convert this angle to be with the positive x? Yes. Why? Because our vector is in the second quadrant. So this is our vector f1 on 3, and this is our vector f2 on 3. Their sum will be on the second quadrant. It will be here, around here. So this is f3. What is our angle? Our angle is, this is the x-axis. This is the angle, alpha. Alpha, it's equal 180 minus 82.5. So it's a, yeah, that's real time. 180 minus 82.5, which is equal to 97.5. 97. So this is our direction. Thank you so much for your attention, and see you in the second lecture. Thank you.